Hello everyone, welcome back. So now the subject I'm going to be talking about is going to be deep learning, bearing the subject code 21CS743. So without any delay, let's get into the video. So the first slide here is basically the introduction, and just keep in mind that all of this particular video is based off of one particular paper that I had chosen. So the title of this particular paper is going to be Robust Active Learning, Sample Efficient Training of Robust Deep Learning Models. So again, as I said, this is the introduction. So deep learning models have actually become foundational in many cutting edge technologies. However, a key challenge is that a large amount of labeled data needed to be trained for these models. Labeling the data is not only expensive but is also time consuming, especially in domains requiring expert knowledge. This is where active learning steps in. It reduces the need for labeled data by carefully selecting which samples to label, ensuring that each labeled data point adds the most value. However, existing active learning approaches focus primarily on accuracy without considering another critical aspects, that is robustness to the adversarial attacks. In real world applications, models are often vulnerable to these adversarial examples, which can drastically reduce their effectiveness. This research is aiming to address this gap by proposing a novel approach, that is RAL, that is robust active learning. This method integrates active learning with adversarial training, making deep learning models not only accurate but also salient yet even robust. So moving on, we have the methodology. So here methodology basically refers to what methods they have actually done. They here are basically the authors have actually performed in order to get the results. So first one is standard active learning. Unlabeled pool of data selected by acquisition, function based on priority, labeling budget determines how many samples to label. Model updated using labeled data to minimize losses. Next one is robust active learning or RAL. Combines active learning with adversarial training, that is using PGD attacks. Models trained on adversarial examples, making them robust. Next one's DRE or DRE, that is density based robust sampling with entropy. Balances clean data performance and robustness. Ensures selected data is perspective of the entire data set by minimizing entropy difference. Moving on, we have the advantages. So the key advantages of this particular approach are improved robustness, that is by integrating adversarial training into the active learning loop, the models are far more resilient to adversarial attacks. Next one is sample efficiency. We significantly reduce the number of labeled examples required to train robust models, allowing for cost-effective scalable training processes. Next one is balanced performance. Our new DRE acquisition function effectively balances clean performance, that is accuracy, and robustness, something traditional methods actually fail to achieve. Moving on, we have the continuation of the advantages. The next one is scalability. Our approach is designed to scale efficiently across larger data sets and more complex model architectures. By reducing the reliance on extensive labeled data and automating adversarial robustness, our method can actually be applied to diverse domain without significant overhead. The next one is adaptive to dynamic environments. Unlike static models, our approach dynamically adapts to new data through the active learning loop. This means that as the system encounters new types of adversarial attacks or variations in the data, it continually learns and improves its robustness, keeping the model future-proof. The last point here is reduced computational overhead. By incorporating adversarial training and active learning in a streamlined manner, our approach minimizes the computational burden typically associated with such techniques, making it suitable for deployment in a resource-constrained environment. So these are the advantages. Moving on, we have the disadvantages. While the benefits are actually substantial, there are some limitations. Firstly, some common used acquisition functions like max entropy as well as EGL perform well in standard settings, struggle in robust active learning. In terms of robustness, they are often outperformed by a similar approach like random sampling, which is a surprising result. This suggests that traditional metrics used in acquisition functions may inadvertently harm robustness. The third point here is additionally, while our DRE function generally performs well, there are certain instances such as with the CIFAR10 dataset and VGG16 model where it falls slightly short random sampling in robustness. The fourth point here is these discrepancies highlight the need for further refinements to ensure consistent performance across different models as well as datasets. So a continuation to this is basically inconsistent performance across models and datasets. While our DRE function generally performs well, there are specific cases such as with the CIFAR 10 dataset and VGG10 model where it falls slightly short. The discrepancy points to the fact that no single acquisition function is universally optimal across all settings. Factors like the architecture of the model and the nature of the dataset can significantly influence the performance of the acquisition strategy. Moving on, we have the potential for refinements. These observations are highlights that need further refinements to ensure more consistent performance across different models and datasets. In particular, the development of new acquisition functions that are more sensitive to adversarial dynamics is crucial for improving robustness in all scenarios. Additionally, more research is needed to better understand the limitations of current metrics and how they can be adjusted to account for the unique challenges posed by adversarial training. The last point here is computational complexity, another limitation to considering the computational overhead introduced by more complex acquisition functions. While methods like max entropy and EGL may offer theoretical benefits, there is real-world application often comes with increased computational costs, which can actually hinder scalability in larger datasets or more resource-constrained environments. Moving on, we have the results. So the results are quite compelling. Across most datasets and models, the DRE acquisition function achieves the best trade-off between accuracy and robustness, outperforming the standard active learning approaches. For instance, on the MNSIT and SVHN datasets, DRE improves robustness by using to 3.84% over random sampling while maintaining competitive accuracy. The next point here is, interestingly, random sampling, though a simple baseline, demonstrated unexpected strength in adversarial robustness, often outperforming more complex acquisition functions like max entropy and LC in terms of robustness. This indicates that the randomness of the selection process might inadvertently contribute to greater robustness, an aspect worth exploring in the future research. So in conclusion, this research sheds light on the crucial gap in active learning, that is lack of focus on adversarial robustness. By proposing robust activities learning, we present a solution that integrates the strength of adversarial training with active learning to create models that are not only accurate but also resilient. While their work set a new standard for balancing accuracy and robustness, it also opens up exciting avenues for further research, particularly in refining acquisition functions to consistently outperform similar and even simpler baselines like random sampling. The journey towards more robust deep learning models continue, but this research represents an important step forward. I hope you understood all the topics that were being dealt in this particular video, and I hope you enjoyed the video. Thank you for watching.